Great. So yeah, I'm here to present this work where we developed a framework to control continuous variable states efficiently using two-level ancillas or qubits. This work was done with, has been done with Steve Garvin, my advisor, and Patis Royer, who is at University of Sherbrooke right now. The problem statement here was inspired by experiments conducted by Vlad Sivak and Alec Eichbush. And this framework finds many uses in GKP qubits. So I'm going to first start with a basic introduction to GKP qubits. All right. So lately, we achieved this beyond break-even result where the QEC gain with GKP qubits was a factor of 2.3, giving you a low of error probability per QC cycle at 10 to the minus 3. This is good because you're below surface code threshold. You could use these qubits in concatenation with surface codes, etc. But before going to that, we need to take care of some additional issues like spam errors, preparation and measurement of these qubits, and gates, etc. So let's first begin with what these states are. The GKP codes are defined in the phase space of oscillators, in the continuous variable phase space of oscillators. This phase space is defined by the position operator, which does not change your state if it has a well-defined position, and momentum operator, which does not change your state if you have a well-defined momentum. So now these two operators sort of define your oscillator phase space. You have your phase space, you can traverse in your phase space. So then I'll define a displacement operator, which will take a real argument to traverse along position, and imaginary argument to traverse along momentum. Now, even though I show the x's and p's on orthogonal quadratures, they don't commute. So displacements along these axes don't commute either. And the Lie relationship given by these two displacements essentially follows this inequality where the A here is the area enclosed by these two displacement vectors. And so if A is a multiple of 2 pi, your displacements commute, otherwise they don't. Now that I've defined the phase space, we're ready to look at the GKP states. I'll show you the zero logical, the displacement operators are basically the following. You can get an intuition of this as follows. So displacement in position does not change your momentum. So it's a function of something that commutes with momentum or momentum itself. And it so happens it's an exponentiated momentum unitary. And so similarly, you can define the displacement and momentum as follows. So now, okay, here's a cartoon of the quasi-probability distribution of your zero logical GKP state, which is basically the Wigner function for those who know this now. The blues here are negative probabilities, and the red here are the positive probabilities. At the bottom, I show the marginal probability of occupying a certain x eigenstate. So the zero logical state here essentially is a superposition of delta functions located at even multiples of root pi. So that's something important you need to keep in mind. Now, this state has some sort of translational symmetry. So if you think about the entire pattern extended over infinite x and infinite p, if you displace the state by, so basically move the state by 2 root pi in x or 2 root pi in p, you'll get the same state back. So that gives us the liberty to define the stabilizers as follows, basically displacement in position and displacement in momentum by 2 root pi. These displacement operators essentially produce the displacement which enclose an area of 4 pi. So these displacements commute as you would like for your stabilizers too. Now define your stabilizers. I'm going to define my logical operators. For that, we'll first look at what the one logical states are. It's essentially the same pattern, but displaced by root pi. So that defines your x logical operator. And in order to think about your z logical operator, you can sort of think of this operator as as an operator which has 0 and 1 logical as its eigenstates, as its plus 1 minus 1 eigenstates. So essentially, a z logical operator should not change this pattern. And so it doesn't. Z logical is basically displacement in momentum by root pi. And the area enclosed by x logical and z logical is essentially, the displacements caused by x logical and z logical is essentially pi. So they anti-commute just as you would like your Pauli operators to. And then we can define my y logical as follows. Okay, I've defined my code. I've defined the qubit encoded logical operators, everything. But I've defined this for a very unrealistic system. I've told you that it's expanding all the way to x equals infinity and p equals infinity, which is not realistic. What I would want is that my state sits within this finite circle where I have finite energy and finite number of photons. So I would want to live within some finite radius circle of this sort. And that effectively changes your delta functions into Gaussian functions. Now, this code deformation from ideal GKP to finite energy GKP is given by this envelope operator, which is a non-unitary operation because essentially you're changing the energy of your system. It cannot be unitary, right? So now this non-unitary operator takes your ideal code stabilizers, which are unitary, and transforms it into something that is non-unitary. You can achieve this non-unitary stabilization using a two-level ancilla, measuring some stabilizer operations on your GKP qubit. Essentially, this is the circuit that we use to approximate that non-unitary stabilizer. Here, my top wire is the top wire is basically a two-level ancilla. The bottom wire is my CV state. And what you see here are three conditional displacements. So if you wanted to measure an operator X, then you would apply a control X gate. Here, I want to measure something that is a displacement operator. So I'm applying a conditional displacement operator. There's three of these. Essentially, the first and the last decide the envelope size. And the middle one is basically the magnitude by which the middle one displaces is decided by your stabilizers. So the first and last, essentially the epsilons here, the conditional displacements by epsilon, these are rather smaller compared to the middle displacement, hence the name small, big, small. And another thing that you need to note here is that the circuit is autonomous. I don't apply any feedback based on the measurement outcome of the ancilla on my qubit. So there's no classical feedback involved. I'm going to come back to this circuit later to describe the same thing in my framework. But for now, that's it. I'm going to now come to my problem statement. So the experimentalist prepared these states. So you have to prepare this state and then sort of study your quantum error correction cycle, how it stabilizes, how it controls your decay rate of the qubit. But the preparation of GKP states is hard. Essentially, say you start off with something very simple like vacuum, which is essentially a blob at x equals 0, p equals 0 in that quasi-probability distribution cartoon that I showed you. You want to start with that state and get to something exotic, some exotic pattern like that, which I showed you. So it's going to be hard to get that. How the experimentalist did this was basically used repetitive patterns of repetitive applications of this gate ECD and rotation. I'm going to tell you what those are on your vacuum state and ancilla in G or 0. I'm going to call the ancilla 0, 1 states GE just to sort of avoid confusion with the CV states. So your ancilla state starts in G, your continuous variable state starts in vacuum, and then they apply these ECD and rotations alternatively to get high fidelity continuous variable states you want, in this case, GKP states, without relying on the measurement. So the important part is you get to the desired state and would have unentangled your qubit from the CV state. Now, the circuits that we got here weren't very intuitive. So the problem statement that we decided to look upon is how can you use this instruction set comprised of ECD and rotations. ECD essentially is your conditional displacement by a Pauli correction. Rotation is basically, this is equatorial plane rotation. You can realize rotation in the z-axis using this equatorial plane rotation as well. So essentially, how can you use this instruction set of conditional displacements and rotations to prepare to do state transfer? State transfer essentially is the problem where you start with your CV state in vacuum and your ancilla in G state and end up with your CV state in the desired state you want and the ancilla with very, very high probability in the G state. So completely unentangled from the CV state. And this is the problem statement that we're looking for. We wanted to analytically come up with constructions for these states and see if we can do something, if we can make these states then, if we can make these circuits then more efficient to prepare better states. Because we have more information about how the circuit, we'll have more information about how efficient the circuit would be if we know what the circuit's exactly doing, and essentially, if there's some structure we can utilize there. So my talk's going to be outlined as follows. The very first bit, I'm going to describe my framework, which is essentially composite pulses in phase space, to study this preparation. Then I'm going to show you how we can use this framework to do state transfer. And then I'm going to come to unitary transfer just for GKP states, because this framework works amazingly well with GKP states. And then finally, I'm going to show you some extension to two CV states, or two modes, which was kind of difficult for the optimizer to achieve, because with a single oscillator, the resource cost is heavy. If you now use two oscillators to do this optimization, basically try to optimize over making a bell pair on those two oscillators, it's going to be really, really costly computationally. So essentially, this analytical framework sort of helps in that generalization also. Okay, let's begin with the composite pulses in phase space. The term composite pulses has been taken from this NMR composite pulse idea, where suppose if you wanted to rotate your qubit by theta about some axis on the Bloch sphere, but due to some noise in your amplifier, etc., you actually apply theta plus epsilon, where epsilon is your error. You can apply some additional pulses, which effectively will apply a minus epsilon rotation, and thus cancel your error exactly. So if there was no error, this pulse will apply identity. If there was error, it would correct this error to first order. And that's essentially what I'm going to do, but in phase space. Okay, so the idea is you want to use your DV ancilla, which can at max give you 1 bit of information. Use this ancilla cleverly to achieve the exact information you want from your CV states. So I said I'm going to correct some rotations using composite pulses. Here, my conditional displacements, which are in my instruction set, I'm going to use that as conditional rotations. I'm going to think of that as conditional rotations on my qubit, and then think of correcting the errors on the rotations of the on the rotations that are applied to the qubit, to sort of see how we can unentangle the qubit or entangle the qubit effectively with the exact information we want from the CV state. So my system, basically, the system that I would apply this gate on would be the hybrid CV state, DV state system. The first one, the psi, is my CV state. The second one, G, is my DV state, two-level ancilla, the G state, in the zero state. Now the CV state here, we can assume for now, is the position eigenstate, which could have a wave function like this. The wave function determines your marginal probability, by the way. In the infinite energy case, in the unrealistic case, the sigma could be 0, and you will have delta functions for your X eigenstate. So your marginal probability essentially looks like this. So if you were located at X equals minus alpha, so if you're looking at position eigenstate at minus alpha, you have a delta function at minus alpha. If you're at plus alpha, you have a delta function at plus alpha. Okay, here in the green, I'm sort of showing the qubit state conditioned on where you are in the CV state. So this is just one qubit conditioned on the fact that you are located at this position in the ancilla. So let's say these are two different cases. I'm looking at these simultaneously. Okay, so I have one position eigenstate at minus alpha and one position eigenstate at plus alpha. If right now I'm completely unentangled. My qubit is in G, be it I'm in the plus alpha eigenstate or minus alpha eigenstate. Now, the idea is, in order to get information about whether, suppose I knew that what alpha is, but I didn't know whether my state is at plus alpha or minus alpha. How do I get this information? So the idea is, you have to do something like this, where you've basically rotated your qubit by pi over 4 to the right, if you were on the left. And if you were on the right, you would have rotated it by minus pi over 4 to the left. So essentially, this is some sort of is already giving you intuition. This, in some sense, is already giving you intuition that I'm trying to entangle the superposition of these two states with the qubit state. Okay, so how would I do this? So if you look at the conditional displacement, if I can use the conditional displacement, which is e to the I alpha x hat, to do this pi/4 rotation in the following manner. Essentially, if I do this displacement by pi/4 alpha at x equals alpha, I would have rotated my qubit by pi/4. If I were on the left, I would have rotated it by minus pi/4. If I were on the right, I would rotate it by pi/4. So essentially, now at this point, if you measure your qubit, it's in G. You know, if it's in plus y state, you know you're on the left. If it's in the minus y state, you know you're on the right, right? But life's not so simple. Sigma is not 0. So when sigma is not equal to 0, I have a Gaussian state. And at each condition on each position eigenstate, my qubit right now at the very beginning is in the plus z state, because right now I'm not entangled. As soon as I apply this conditional displacement, what happens here is at exactly the peak, I did exactly what I wanted. So for the left state, I'm at plus y, and for the right state, I'm at minus y. But everywhere else, it looks like I've over-rotated or under-rotated. So if I were just looking at the state, at the left state, I'm not completely in one single state of the qubit. And if I'm looking just at the right state, I'm not in one particular state of the qubit. So the qubit measurement outcome is going to give me some ambiguity. That is some chance that even if I'm on this side, I will still get, say, minus y and plus y both. And I don't want that. I want to do this efficiently such that the same thing that happened for delta function happens for Gaussian functions. So the idea is I want to correct for these over rotations and under rotations that happen here. So essentially, within this region, you have under rotations. Outside of these regions, you have over rotations, because here your mod x is less than alpha. Here and here, your mod x is greater than alpha. So the error here is pi/4 alpha x minus alpha in rotation, right? In order to correct this rotation, I need to apply something like e to the I x minus alpha. This is not available to us. But if you think about what position operator is in the, in what momentum operator is in the position basis, it's just a derivative operator. And I'm looking at Gaussians here. So what's the derivative of the Gaussian function? It's x minus, so if you have your, if for this particular state, if your sigma is 1, my derivative would essentially be proportional to x minus alpha times the Gaussian, right? And essentially, this is the thought behind correcting this rotation. I'm going to take the same state, the top one, and apply a rotation, a conditional displacement along P this time. Now that essentially, sort of what it does is, you can see that at the very center of these peaks, you're not doing anything to your qubit, but over here you sort of rotated in this direction, which effectively will cancel the under rotation. So you kind of will do this extra rotation to patch this under rotation. Over here, you've rotated to this direction. So this is basically anti-clockwise. And essentially, you can see that you need an anti-clockwise correction to correct for this over rotation. And the same thing happens over here as well. Now, to get a more mathematical picture of what's happening here, what you can do is you can expand this conditional displacement unitary in the following for large alpha as follows. And I've replaced I p hat by del over del minus del over x. Now, this looks like a non-unitary operation. I don't have my I, right? But if you think about what sigma y does to your G state, which is basically the starting state of my hybrid CVDV state system, sigma y is I sigma x on G state and minus I sigma x on E state. So it's this, essentially, if it's this property that I will use to say to conclude that this specific conditional displacement performs the following rotation. It performs the rotation proportional to x minus alpha about the exact axis actually I wanted, because this sigma x is what will cancel the error in this rotation, because you need your Pauli axis to be the same to actually correct for each other. So now I'm going to define my entangling gadget, which is what I call it, coming from complexity and algorithm's point of view. I'm going, this is basically, you apply correction on the G state, That's because you want, the correction has to be applied to the G state, like I said. If you apply it to the E state, it's a different correction. So the correction has to be applied first. So you've sort of opened up your qubits in the way you wanted. So it's a pre-correction you're trying to apply. And then you apply the target unitary you wanted to, on which you were applying this correction. And then you will see that effectively what you would have done to the delta function, now you will do that to your Gaussian functions. So again, going back to the math, if I just applied the target unitary, then it's essentially this state you will get, which is basically the target rotation that I wanted to achieve, depending on alpha being the peak of your Gaussian state, and this being the error x minus alpha. Now, if you apply that correction unitary onto the psi tensor G state, like I said, over here, assuming that epsilon is really, really small, I effectively get the following gate, which I can then write as, if I apply this derivative operator coming from the momentum operator on the Gaussian state in psi, I get the following expression with x minus alpha, which then I can write as a non-unitary rotation about I gamma. So what does it mean to have your rotation axis as I gamma? We just need to see what exactly should be these values such that I exactly cancel the error over here given by x minus alpha, right? So this error would be exactly canceled if my epsilon is theta sigma square, so for arbitrary sigma, and sigma gamma is I sigma phi. And there basically I use that state dependence on my correction unitary. So if your sigma phi was sigma x, then your sigma gamma will have to be I sigma x, which is basically sigma y sigma z. So a state dependent correction. So this is what my entangling gadget would be. To think about what the unentangling gadget should be, it's just the reverse of this circuit, not inverse, but the reverse. Because inverse is a more restrictive word, I would say, because all you need is that. So our quantum circuits are reversible. I can just think of starting from here and going all the way going in this direction. So my correction unitary has to be applied to the G state. So here I'm saying that at the end of the unentangling circuit, my qubit will, with maximum probability, be in G state. If it's in G state, then only is the correction doing the right thing. If it's in E state, it's not doing the right thing. So with maximum probability, I want to be in the G state at the end of the circuit also, and that is guaranteed by this. That will be guaranteed by this target unitary. So the target unitary would ensure that with maximum probability, you will be in the G state. The correction unitary just applies a first order correction due to the quantum uncertainty that we have. And there you go, you have your unentangling circuit as well. The inverse would actually mean that you would need a minus I theta there and a minus epsilon there. No, you can go by theta and come back by minus theta. But you can also go by theta and come back by 2 pi minus theta. So that's the idea. The second one is not the inverse.
Why wouldn't you do the inverse though?
Oh, you can do the inverse, but there's some more. What I'm saying is there's more independence in choosing theta and epsilon rather than it just being the inverse of this circuit. And I'll show how actually I'm going to use that property. So, okay, let's come to the solution to a few solutions that this framework provides now. State transfer. I'm going to talk about the cat state preparation, deterministic cat state preparation. So far the cat state preparations are dependent on your measurement outcome, but my scheme would show how you can make cat states without depending on the outcome of your ancilla qubit. And then I'm going to talk about the logical GKP magic state preparation, which they did not optimize for in the experiment. They just optimized for logical Pauli eigenstates. So for deterministic cat states, okay, if you don't know what cat states are, it's fine, because whatever I'm going to show you on the slide is all you need to know. So you start with your top wire in the vacuum state and the bottom wire in your ancilla state being in the plus, ancilla qubit being in the plus state. At this point, you are basically at x equals 0, p equals 0 in the phase space in terms of vacuum, and your qubit basically is pointing, oh, yeah, no, the qubit should pointing outwards, but you get the point. Now I'm going to apply a conditional displacement by alpha, which will take this one blob into two blobs in this manner. And at this point, you're entangled with the qubit. So cat states are basically superposition of these two blobs. Plus superposition is even cat, minus superposition is odd cat. And these two blobs are basically called alpha and minus alpha. These are coherent states. You don't need, if you don't know what coherent states are, no worries. Okay, so now at this point, what people generally used to do was measure your qubit in the measure your qubit in the x basis, get alpha plus minus alpha or alpha minus minus alpha condition, the outcome being plus or minus. But what I'm saying is exactly this is the kind of situation I can attack with my unentangling gadget, right? So I'm going to append my unentangling sequence. And at this point now, in the CV state, I have my even cat always. And in the ancilla, I will have, my ancilla will end up in the plus state with very, very high probability. So even for the worst case, it's like 0.90. All of this, again, without errors. I'm not discussing errors here. Right, so basically this sort of indicates that that I've managed to unentangle my qubit from my CV state. So I'm going to plot here the cat size alpha and show that as it increases, like I said, my assumption was based on the fact that alpha should be large. As it increases, this protocol works much and much better. For now, you just have to focus on the blue and the greens. The blue shows the state infidelity for even cat state. And the green shows the one minus the probability of getting a plus state here. So you want both of these to be low. And as you can see, as I increase alpha, it amazingly goes to all the way up to 10 to the minus 7. I mean, I know alpha equals 10 is large, but this is essentially what the CVDV unentangling circuit is doing. And your probability of getting a plus state is also increasing, so that 1 minus the probability is essentially decreasing here amazingly. Now, you would think that, oh, this works only for large cats. What about small cats? Like, what about this region? So I have I won't discuss this protocol, but I have a protocol to do that as well. And that essentially looks like this. So for the small cats, again, the 1 minus probability and the state infidelity go all the way up to 10 to the minus 6. As you decrease alpha, as you increase, this gets bad because this protocol is for small cats. It doesn't work for large cats. The problem is essentially this middle point, where you're neither a large cat with non-overlapping Gaussians, nor a small cat where your state looks like squeezed vacuum or something. So the same blob that I showed you, but like squeezed in one direction. So it's like a, what do you call that? Yeah, oval. So but even for those cat states, I have a protocol. Again, I'm not going to discuss that because I don't have time, but it's not very trivial. So essentially, that sort of indicated that this framework, this ECT instruction set, is very good for the cases where your Gaussians are not overlapping, for example, which is the case of GKP states and large cats. And now let's look at the GKP magic states. GKP magic states are basically the Hadamard eigenstates. Since your X logical and Z logical are defined on X and P of your phase space, a Hadamard basically exchanges these, right? So Hadamard eigenstate should not change when you exchange your X and P. Essentially, that's all you need to know. So the pattern that I will show you that will correspond to the magic state will be invariant if I exchange X and P. Okay, so what I do is I start with my vacuum and plus state. So I've written plus tensor 3 because I'm going to do the same thing thrice. Doesn't mean you need 3 qubits for it. You can just use the same qubit over and over again. That's what essentially we'll do in the experiments, I guess. So I use the same deterministic cat state preparation that I showed you earlier here, where my alpha is square root pi over 2, given the GKP state lattice spacing. So I use the same protocol thrice. I take my qubit and plus state, apply that protocol, reset it. Don't care about the measurement. Because I'm conveniently saying that the measurement outcome will be in the plus state with maximum chances. And after doing that, I've basically, like I said, one of these would create 2 blobs, 2 of these would create 3 blobs, and you will get to 4 blobs. So I've created this sort of expanded lattice in just X. GKP states are expanded lattice in both directions. So I need to next intuitively do the same thing in the P direction. In the P direction, what happened? Oh, yeah. So the probability of getting plus states in all three runs comes out to be 0.97, not 0.99, but yeah, Then I'm going to expand my lattice in the momentum quadrature. And here, I can't do the non-unitary correction that I've been talking about, essentially because now I'm sort of expanded all the way in X. So that sort of has a very bad back action on my state. Maybe we can correct this back action in some sense. I haven't figured that out yet. But you expand this lattice, and there goes your GKP magic state. This is basically a magic state. And you've done this thrice. The probability goes down to 0.92 here, essentially because I'm not able to apply those non-unitary corrections. But this is it. Like here, only the probability of getting plus state at the very first round of this momentum expansion is 0.94. Everything else beyond that is 0.99, 0.99, 0.99, and that multiplied together gives you 0.92. Finally, I haven't talked about the envelope at all here, right? I've just taken a state, started preparing. Started using the cat state protocol in X and P and got the grid state. To sort of fix the envelope size that I talked about, I will just use the stabilization scheme of GKP because now I'm already in the code space. So the process will not be random. The process will stabilize things and correct for the small errors due to the envelope. So I'm just going to use the SPS stabilize, the small big small protocol once, and I've fixed the size at, say, photon number at a point where your CV state will only have your CV state will only have 8.8 photons on an average. So that sort of gives you the GKP state with the right envelope size. If you look at it carefully, the state on the right is slightly smaller than the state on the left. If it's not very evident, don't worry about it. Yeah, I tried to make it look smaller, but yeah, I guess I should have gone to lower ends. Okay. So all of this now, so at the last point, it's basically you get plus outcome with probability 0.98. This is important because, oh, sorry, go ahead.
Oh, sorry, I was just going to ask
why do I need? Oh, because here my photon number is not fixed. So suppose your protocol was designed for a specific photon number, you need to go to the code space of that finite energy GKP with that specific envelope size. This here is not fixing your envelope size. I mean, my photon number perhaps is not at 8.8 here. I mean, I'm sure it's not 8.8 here. Yeah, so yeah, exactly. Because in these experiments, you will optimize this delta, the envelope size, and you want to get to that specific alpha. Delta. All right. So the thing to note here is that the SPS protocol is a random protocol. If you started from vacuum, you will get to the GKP state if all outcomes were G for like 8 rounds of the SPS protocol. But this has a horrible success chance because at the very first round, you're creating this even cat odd cat with 0.5 probability. So the very first round, the plus outcome, you get the plus outcome with 0.5, then 0.6, then 0.7. Multiplying all of this together for 8 rounds gets you to 0.07. Horrible success probability. Here, applying SPS at this point is 0.98. That means that I'm already in the code space. And the whole thing, the success probability is 0.88. So much better than just using SPS and doing post-selection. And the state fidelity at this point is 0.995. Now, that was the logical magic state. What about logical Pauli eigenstates? So for the Pauli eigenstates, things are much simpler. So I'm just going to talk about one of those. Let's talk about the states which basically I showed you, the 0 logicals and the 1 logicals. So for that, you won't start with vacuum. You start with squeezed vacuum. So it's basically a state stretched in X and squeezed in P. Stretched in P, squeezed in X. And if you run the same protocol only twice on that squeeze state, you get the GKP logical 0 state with success probability of 0.99. So you will easily make 0 logical states and plus logical states with this scheme. And yeah, so I think Ben Marjola has this paper where he said if you have multiple copies of 0 logical, you can achieve magic states, distillable Hadamard magic states. So you can actually use these multiple of these 0 logical states also to do magic state distillation. All right. Okay, now we come to unitary transfer. So like I said, this framework works really well with GKP states. And I'm going to first discuss how the stabilization scheme can be looked at from using my framework. Then I'm going to show some gate teleportation circuits, and I'm going to show that this gate teleportation circuit actually is also correcting errors on your oscillator. So let's get on with that. So that's my small with small protocol that I showed you already. Now, this protocol can be divided into two halves. I've basically broken down the middle conditional displacement into two halves. The first half is my entangling circuit, if you recall. And the second half is actually my unentangling circuit. If you are in the GKP code space, this circuit will basically apply a logical identity on your space. Basically, this entangling and unentangling works only correctly if you are in the GKP code space. Okay, yeah. So yeah, if you are in the 0, 1 logical space, this stabilization essentially entangles the qubit with the 0, 1 logical state. And then this other circuit basically unentangles it. You can think of it as this gate essentially applying a pi rotation if you were in the 1 logical state, and a 2 pi rotation if you were in the 0 logical state. So that's why this entanglement. And the second half, applying another pi rotation, 2 pi rotation. So now you have 4 pi rotation and 2 pi rotation. Both of those will end up with plus and plus, which is what you see here. There's a minus sign that we acquired here, which is basically a logical Pauli, which we know that SPS applies. It's a deterministic Pauli. It's not an error. Okay. So now we can now we need to think about how about when we're not in the GKP code space, right? What then? So in that case, you can get an outcome of E, and I told you that if you get an outcome of E, this unentangling circuit will not work correctly, because at the end you have E and you're applying a wrong correction on it, right? So you can sort of think of breaking down that last displacement, last conditional displacement, which is a correction for the unentangling sequence, into these two forms. This part essentially is the correct correction for the E state. So I've split essentially that gate into a correct correction on the E state and a conditional displacement. So you can think of it as, at this point, your qubit, if eventually you got an outcome of E, then your qubit at this point was in E, and you applied a conditional displacement when after that. So this is like the adaptive phase estimation correction that Barbara Terral's protocol applies. And I never understood how the dissipative stabilization scheme does this correction. And now with this framework, this is actually pretty clear, because this correction is exactly what Barbara applies in her adaptive phase estimation schemes. Okay, now, okay, so I told you that I'm going to give you a gate teleportation circuit, right? Let's just take your GKP and GKP qubit and your plus qubit, entangle them using the first half of SPS, apply some rotation, apply a specific rotation on your qubit, and then unentangle your GKP and plus qubit. So essentially what I'm doing is, at this point, I've entangled my GKP state with the plus minus qubit. Then I apply an x of theta. So it's important that you apply the x of theta rotation, because I want the phase on the plus and minus states that I'm entangled with as the GKP myself. At this point, I've applied the qubit gate, and that sort of applies this phase here. After that, the unentangling circuit will basically rotate the plus qubit by 4 pi, the minus qubit by pi, and thus you arrive at this state, and your qubits in plus with your GKP qubit having a logical z theta gate with an added Pauli correction. We will ignore that in all the circuits I show you. So we've got a logical z theta. So if you entangle your qubit with the 0, 1 basis, you get logical z theta gate. Now, if you do the same thing in the plus minus basis, so you take the GKP qubit in the plus minus basis, the stabilization circuit in the other quadrature. So this is the stabilization in X. If you use the stabilization in P, you're basically entangling your ancilla qubit with the plus minus basis, and you get this circuit. In this case, you will be applying a logical x theta gate. So now I've shown you how to apply a logical z theta gate, how to apply logical x theta gate. Similarly, you can do logical y theta gate also. But I've shown you how to do arbitrary single qubit rotation using this gate teleportation mechanism. Okay. And all of these are, so the success chance of, so the idea is that at the end of all of this, the qubit should be in the plus state if there was no error. And the success chance basically denotes what's the probability of you getting a plus state there. That's 99.88%. And the fidelity without any error is 0.9994 for all of these gates. So I just checked the state fidelity. I guess there's a better metric to quantify the gate fidelity that I should be using. But for now, I just check the final desired state that I would have wanted upon the action of the gate. And the fidelity comes out to be 0.9994. And I check this for x theta, z theta, y theta, all of it. All right. So now I said that this gate teleportation circuit is sort of an error-corrected gate teleportation. To see how that's true, I'm going to bring you back to how you would do this in a trivial fashion. If I were, this goes back to Stephen's question as to what's the problem with doing an inverse, right? I could entangle here, apply this gate, and then unentangle by just applying the minus. This circuit is not the SPS circuit. It doesn't do error correction, because if you started with an error state here, this circuit does not identify any errors in this circuit. Essentially, if you think about the composite pulse idea, if I go by theta and I use a corrective rotation by minus theta, that doesn't correct your errors, right? The correction can come only if you're doing a 2 pi minus theta. So you're going all the way around the circle. And that's essentially what the error-corrected gate teleportation does. It rotates your qubit entirely by 4 pi and 2 pi, given you're in the 0 logical or 1 logical state. If you're in the code space, if you're not in the code space, this rotation doesn't go around. Like, you don't get the 2 pi rotation or 4 pi rotation. You get that autonomous error correction that I talked about. And that would still be valid here, right? I haven't changed anything about the entangling and unentangling circuit. So this circuit is an error-corrected circuit. It gives you an error-corrected z of theta gate. And all of this assuming that you don't have errors on the ancilla for now. Okay, now let's think of what happens when you have ancilla errors. As soon as you have ancilla errors, this circuit basically makes no sense to use, because the original SPS circuit, the small big small protocol, was good in a way that if you had something like bias noise where your sigma z errors were much higher than sigma x errors, there's a chance of fault tolerance with such noise, such ancilla noise. Here, I've sort of broken that symmetry by just applying this x of theta rotation, because if I have a sigma y error over here, which commutes with this gate, if I teleport it all the way here, it will not mess up this gate, but it will mess up this rotation. It will take it to x of minus theta. So instead of applying x of theta, I would have applied x of minus theta. Not good for me. And there's no way around it. So why am I talking about this gate teleportation circuit at all? So that's where essentially the property of the gate teleportation being error correcting on the oscillator comes into picture. I'm going to use a model. It's a model where I break this rotation into m parts. The term piecewise is taken from Ted Yoder's piecewise fault tolerance, but it's not piecewise fault tolerant. It's just a method to sort of distribute this gate into pieces such that I am least affected by ancilla errors as much as possible. So I'm not doing anything to do error correction. I'm just trying to sort of minimize the effect of this dephasing error on my gate. So the idea essentially is that in the absence of error, you would have applied RZ of theta. In the presence of error, you would have applied RZ of minus theta. You don't get a logically orthogonal state, right? So there's still some overlap with the desired state you want. So the idea is, I'm gonna divide my x of theta rotation into m parts. As such, after each part, I will measure my qubit. So this is something in some sense like Zeno circuit, if you know about it. So essentially, you can think of this circuit as a toy model with 2 qubits. Actually, like I said, I'm not doing anything with GKP to do this, to tackle this error. It's a very simple 2-qubit model. There's a very simple 2-qubit model explanation for this. So at this point, I am entangled in the specific state 0 plus 1 minus, right? So I'm going to take 2 qubits in the plus state, entangle them with the control Z state, and with the control Z gate. At this point, I have my state in the exact. I have my 2-qubit state in the exact CVDV state over there. So 0 plus 1 minus. G plus E minus. I said that G, E are my 0, 1 for the qubits. And then I apply my x of theta over m. Then I do the unentangling bit by control Z operation. And then I reset the qubit. So this is the toy model we can sort of use to explain whether this piecewise application would work or not. So this sigma y will correspond to applying a sigma z error over here. This does the same thing. Commute the sigma z through. It does not affect these conditional gates, but it will affect the rotation. Now, what I do is, so if you have a single Z error, the error that you will get this time will be minus 2 theta over m instead of minus 2 theta, right? But the downside is that I've increased the number of times this error could happen. This error could happen m times, right? So that's the downside, but there's an upside that you're sort of you're sort of closer to your desired state, because the error is just minus 2 theta over m for every first order error. So like if you had just single Z error in your circuit. So then what I'm going to do is I basically used this toy model. On the x-axis, I plot m. Basically, I use increasing m's to justify whether this gets better or worse. For the left graph, sorry, yeah, right. For the right graph, I plot the 1 minus state fidelity, and on the left graph, I plot 1 minus the purity, because the idea is that if you're resetting m times, you're getting a class. You can think of getting a classical mixture of density matrices with single Z error, 2 Z errors, 3 Z errors, and so on. So I just wanted to check how the purity of the state goes about. So I just plot like trace of rho square, for example, 1 minus trace of rho square. So for the state fidelity, here's what I get. So the reference is, if you did this in a single shot, that's the infidelity you will get. If you did this in m rounds as such, the blue curve shows how you've reduced the effect of dephasing on your desired state. And in order to understand what was happening, I've shown a calculation graph also. This calculation essentially is the same idea. I calculate the fidelity of this classical mixture of states comprising of single Z error, 2 Z errors, 3 Z errors, and so on. And that expression comes out to be the following. You plot this, that's the orange curve there. So I've justified that this actually works. And if I look at the purity also improves with m rounds. So you can just think of this as on a more philosophical level as applying adiabatically small amounts of rotations while applying SPS circuit, because if m is really, really large, then your rotation is very, very small. And so it's almost like you have a theta tends to 0 limit where exactly this gate teleportation circuit is your stabilization circuit. So m being large actually gives you the stabilization circuit exactly. Okay, now I'm going to show you how this works for the actual system. So on the x-axis, I plot 1 minus state fidelity for the GKP gate operation. And on the x-axis, I have the number of rounds as I increase. So there will be a blue curve, which will show if I just did 1 round of trivial gate teleportation, the one with inverse and no logical identity. If I did this for 1 round, and for the m minus 1 rounds, I'm doing stabilization. So this is like the right thing to do to actually compare with what I'm doing here. Because why would your qubit be sitting for the m minus 1 rounds? You can apply stabilization, right? And then there's an error-corrected gate teleportation circuit. Basically, I apply the one-shot error-corrected gate teleportation and then do m minus 1 rounds of stabilization. Then there's PECGT, the orange curve, which is the piecewise circuit. I've applied this into m chunks. So I've sort of divided my rotation into m chunks, whatever rotation I'm doing. And this rotation was actually for the T gate here that I'm showing you. And the previous one was also for the T gate. I forgot to mention that. And then in the red one, I show the stabilization. So the graph should be taken for qualitative purposes. So my red curve should be the best I can do. So matching this curve essentially means you're matching your gate teleportation circuit with your stabilization circuit, the same stabilization circuit that was used for the beyond break-even experiment. So here's what I get. The blue curve all the way to the top, slightly better than that, the green curve. So it's the error-corrected gate teleportation. My stabilization curve is the red one. And you can see how close the piecewise circuit gets here. And now you'll claim that, oh, but you're not doing error correction because there is no error on the oscillator. You're just applying ancillar dephasing noise. But no, the ancillar dephasing actually messes up the last rotation. So you're applying small errors on your circuit. So if you leave your circuit for like 20 rounds, as I've shown here, if I did not do anything. So for example, if I just broke down the trivial gate teleportation circuit into m chunks, the infidelity would go crazy. It will basically be a linear curve all the way up. But here, it's actually going to a plateau and is the closest possible thing on this graph to the stabilization scheme. And that's sort of also an evidence that this is indeed an error-corrected gate teleportation circuit. Right. Finally, we'll get to the two-mode extension. Like I said, the extension to two modes is resource cost heavy. You don't want to optimize this. So it's better to get an analytical framework and attack this problem. I'm good on the time. OK. So first, I'm just going to show the trivial two-qubit gate teleportation. You can take the same gate teleportation. For the top qubit, you entangle your GKP state with the ancilla in 0-1 basis. For the bottom one, you entangle it in the plus-minus basis. And then you just have to apply a control Z gate on between your two qubits, and you get your GKP state after the disentangling or unentangling circuits. And that's actually good because the control Z gates are fast on the transmons, right? Here also the ancillar dephasing problem comes about. Like if you have an ancillar dephasing error at the control qubit, ancilla, then you will affect the target ancilla, which effectively will transfer a Pauli error on the qubit, GKP qubit. I could have studied the similar Zeno kind of thing. I have the expression for it, but I don't need to, because I can actually get the exact finite energy circuit for the sum gate, which is in fact much better. So the exact finite energy sum gate is basically the entangling gate, the logical entangling gate for the finite energy GKP states. The ideal gate, you can think of it as this way. You just apply e to the I x tensor x. So if you were in the 0-1 logical state, if you had delta functions, then you are at even multiples of root pi, right? So this expression would become e to the I even multiple of root pi x hat. That means on the second qubit, you're basically applying a displacement by 2 root pi, right? But one, I don't have delta functions. Two, this periodicity only holds for infinite lattice. It doesn't hold for my finite energy GKP. So here, I derived the circuit the same way that SPS was derived, and I can actually justify this using my composite pulse argument also. But I'll just show you the circuit here. The circuit essentially is you apply e to the I x tensor sigma y. Introducing the qubit brings you the periodicity you needed, because you transfer that 2 root pi factor as a 2 pi phase on your qubit, and the rotations are periodic in 2 pi, right? So that's sort of the sense of bringing the qubit in here. And then the correction you need looks something of this sort. The delta square is basically, again, decided by your envelope size. So this operation is small, like it's a small, when I say small, it's faster to do. And this, the green one is the larger gate. So this circuit is essentially fault tolerant to bias noise ancilla, exactly like the SPS circuit was. So I don't actually have to worry about the gate teleportation circuit and study ancilla dephasing for that, because this already solves the problem. So it preserves the periodicity of my finite energy lattice, and it preserves the envelope, because if you just did the e to the I x tensor x gate, the fidelity of that in the absence of error, all of this in the absence of error, if you apply just the ideal gate, the fidelity of bell pair is 0.70, ridiculous. And if you use this gate, the fidelity comes out to be 0.96. It's not 0.99999 because the back action due to the delta square here is sort of worse than it is in the case of SPS. But it doesn't mean that you cannot increase it to 0.99. You just have to apply some stabilization rounds, and you will get back to higher fidelity. But the point is that for the ideal circuit, the number of stabilization schemes you have to follow it by would be much more than the finite energy gate. So with this framework, I was able to get analytical circuits for ECD optimized state transfer. I showed you the state transfer for GAT states and GKP codes. I have actually a better end-of-the-line readout mechanism for GKP states, but given the time, I cannot discuss that yet. But I'll be happy to chat if you're willing or interested in that sort of thing. I showed you a piecewise error-corrected gate teleportation circuit, which is only possible if you have an error-corrected gate teleportation circuit, which was again only possible with this analytical circuit framework, composite pulses and phase space framework. And finally, I gave you an easy extension to unitary optimization to 2 modes, which was going to be really expensive in terms of resources or computationally if you were to optimize these gates and states. Okay. Thanks.
Any questions?
In the CK Teleportation protocol, so the zero, it seems that the overall design is some of your number of steps. So what about errors on this?
Sorry, yeah, so like I said, that circuit was error correcting. That's the gate teleportation circuit was actually error correcting on the oscillator error, sorry, on the CV state errors. So like I said, it was a logical identity. It was correcting the errors in a similar fashion that the stabilization circuit was, because you will go through a rotation by 2 pi only if you were in the GKP code space. If not, in the end, you will still be entangled with the ancilla and will be applying some autonomous error correction, just like the stabilization scheme does. So that's how this circuit takes care of oscillator or CV state errors. So I've checked this for oscillator errors also, and the circuit performs really well. I just did not show it because as soon as you apply oscillator errors, the distinction between how this performs very well against dephasing is not very evident, because all of them sort of converge to very similar, very close curves.
So I guess going back to the original scheme, so you talked a lot about correcting the back action on the oscillator mode. How much do I have to worry about the back action on the qubit itself? And you talked about reuse that resource intensive, level 1 time scales.
You cannot do these operations simultaneously anyway, so you'll have to do it in succession. These circuits are long. So the idea is that since the probability of getting a plus state is very high, if you got a minus state, post-select, because that means you've had an error in the circuit.
And I guess building on that, these echoing techniques work from a quasi-static assumption. You assume that sort of you rotate by similar amounts. How long time scale wise are these interactions, and does this quasi-static assumption break down at some point?
It's, I think, microseconds, if I remember correctly, the conditional displacement. It's
a good assumption of the rotation, opposite.
Yeah.
Yeah, I had 2 questions. Gavin asked one, and I forgot the other one.
Okay. Right.
So yeah, I guess also how much analysis have you done on errors on the ancilla during this process? How is the propagation of the ancilla?
So I already showed you how the ancilla dephasing affects these circuits. Ancilla decay would generally be bad because the stabilization circuit from which these circuits originated from, those also don't work really well with decayers, because the problem with decayers is that as soon as you have ancilla decay, that is a bit flip. So it's not bit flip, it's a combination of sigma x and sigma y errors. It stops your conditional displacement. You are not able to finish that conditional displacement. There's no way there's no going around that unless until you have a fault tolerant conditional displacement scheme, which we don't right now. So yeah, there's no protection against decay, sadly. But yeah, if you have bias noise ancilla, then which is why I basically did this analysis for dephasing only, because we have some chance with bias noise ancilla.
So are you optimistic about that? So if I was thinking about, say, an application in optics instead of superconducting qubits, I would be mainly worried about loss on the 2-level system and the optical mode. And so you're sort of saying, the scheme as it stands is not well designed to tolerate.
Yeah, I wouldn't want to use ancillas there.
And so do we know, so would you be optimistic that there's a modification, or is it really intrinsic to the approach?
There could be better preparation schemes in that case where you don't need, with some beam splitter interactions, you could actually get something similar, which I tailored the circuits such that your qubit gets unentangled and you get the desired state. There could be some sort of an analogous approach in optics also. I haven't studied that. But yeah, I mean, if your answer noise is extremely bad, there is no chance these circuits will have or these qubits will have currently.
Intrinsically.
Which is what your bias noise, your Kerr-Cats are, right? So that's like, if you have bias noise ancilla, you're good. Well, good theoretically, we'll see if it, yeah, hopefully it will work out experimentally as well.